So today we're going to deal with the pump performance characteristics. So a few basic things that we kind of have already seen dealing with pipes. Pump head rise, so actual head rise is the difference in pressure, P2 minus P1 over gamma. Difference in velocity, V2 squared minus V1 squared over 2G. And then difference in height, Z2 minus Z1, so it's basically just the standard Bernoulli equation that we're used to. Typically in this case, the pump only serves to add pressure to the system. You generally don't have much of a velocity gain. Conservation of mass is kind of hard to change the velocity. So pressure is pretty much one thing that changes, and then that pressure can serve to increase the height of the pipe further down the line. But in terms of the pump itself, generally doesn't go very high, just across the pump. So generally just increasing the pressure from the pump. Power transfer to the fluid. Again, we saw this a few weeks back. Power is gamma times Q times the head, in this case HA. And the overall efficiency of the pump is basically power out divided by power in. So power gained by the fluid divided by the input shaft power to the pump. So basically this guy here divided by my W dot shaft. So overall pump efficiency, we just saw was reduced by the hydraulic losses in the pump, so that's the one we just kind of went over. But it could also be reduced by any sort of mechanical losses through the bearings or seals, as well as possibly some leakage of fluid called volumetric loss. So the overall pump efficiency is actually a factor of these three efficiencies. We have the hydraulic loss, the mechanical loss, and the volumetric loss, or volumetric efficiency, mechanical efficiency, hydraulic efficiency, all multiplied together gives the overall efficiency for the pump. So the pump performance, as mentioned last class or last lecture, is generally given by these performance curves that show the relationship between the head, the efficiency, and the power, all versus flow rate. So how the head depends on flow rate, how the efficiency depends on flow rate, and how the power depends on flow rate. And a lot of times you see these all presented as one graph. So all three curves on the same graph. These are again for some particular geometry, so some particular diameter of impeller and some particular rotational speed. So as you change the diameter or change the rotational speed, you're going to be changing these curves. So these are always, again, for some very specific pump in terms of diameter and some very specific operating speed as well, rotational speed omega. So a couple key points on this graph. The first one is where my head hits the y-axis, or zero flow rate. That's called the shutoff head. So zero flow rate is shut off, basically close the valve, don't let any fluid come through. So that's the head at zero flow rate. Now that obviously should be, the pump should not be operated in that state for very long, because basically there's nothing coming through. It can't suck any fluid through because the valve's closed, so that's not good for the pump. Maximum efficiency. So where my efficiency curve hits the maximum, that is called the design or normal flow rate. So that's basically where you want to have the pump operate, because that is the maximum efficiency. That's what's going to cost you the least amount of money in terms of energy input. So that can all help with pump selection. If I have a certain desired flow rate, I want to make sure that whatever pump I choose has a design flow rate that's close to whatever flow rate I'm looking at, so that I can take advantage of having that at that maximum efficiency. And again, not just with what pump to use, but also what rotational speed, because as I mentioned, these curves are all going to change based on rotational speed as well. So in terms of pump selection, in terms of the actual pump itself, as well as how fast to turn the impeller. Another important parameter for pumps and pump selection is called the net positive suction head, or NPSH. So basically what happens with a pump is it is sucking this fluid through it, and because it's sucking the fluid in, that lowers the pressure on the suction side. So on the suction side of the pump, you have low pressure, and that pressure becomes low enough. If it's lower than the vapor pressure of the liquid, that liquid is going to turn into a gas, and that's not good for the pump. Pumps are made to pump liquids, not gases, and so if you try to pump a gas with a pump, it's going to end up not only having very low efficiency, but also possibly causing damage to the pump itself. So we want to avoid cavitation. So that's what NPSH allows us to figure out whether that's something we need to worry about or not. So NPSH, net positive suction head, is defined as the difference between the total head on the suction side and the vapor pressure of the liquid. So basically, again, want that to be a positive number, and the higher the better, because the higher that is, the further away we are from cavitation. So on the suction side, total head is pressure over gamma, v squared over 2g, plus my height. Height is usually taken to be 0, so total head on the suction side is usually just these two terms. And then my vapor pressure head, the vapor pressure of the liquid divided by gamma, is that guy. And that gives me the net positive suction head. So getting into pump selection, first thing you want to realize is that I have a mechanical energy equation. Same thing we've always seen, Bernoulli equation. P2 minus P1 over gamma, V2 squared minus V1 squared over 2G, Z2 minus Z1 plus the head losses. That is the pump power essentially. So my H added for my pump is equal to all that stuff. Important thing here is that my head loss, HL, we know from the pipe lesson that that's proportional to velocity squared. So this was FL over D times V squared over 2G, or for the minor losses, it was K times V squared over 2G. Either way, it was proportional to V squared. And velocity is basically the same thing as flow rate. Again, proportional to flow rate in terms of the area. Remember the curves we had before with the pump performance curves? They were a head curve versus flow rate. So basically what I want to do is see how this depends on flow rate. So essentially what I can do is replace all my V's with Q's and just have some other constants in there. And so I have some terms that depend on V squared basically, this guy and this guy. Those guys are going to be depending on Q squared. Some terms that do not depend on Q at all, like this guy and that guy. And so those are just going to clump into another constant. So I can write this equation as a whole bunch of stuff that doesn't depend on Q, and a whole bunch of stuff that depends on Q in this very specific way, depends on Q squared. And so A and B are just constants with respect to flow rate anyway. And so my equation for the pump power that's added in terms of head is just some constant A plus some other constant B times Q squared. And that comes from this equation. Again, that A and B is just appropriate terms for that equation. So those constants A and B in that equation are determined by the system. In other words, they're determined by the terms in the equation. Things like pressure and the height, those go into this constant A. And so depending on what sort of pressure difference or what height difference I need the pump to do, that's going to be in that parameter. And then the other things, V squared over 2G and all those head losses, all the other terms are going to go into my constant V, which is proportional to Q squared. So I end up with my overall head, A plus B squared, A plus B times Q squared. That's called the system equation. And so if I plot that system equation, it ends up being a quadratic, like this purple line here. So I have A plus some constant B times Q squared, so I get that parabolic shape. If I plot that along with the performance curves that we saw before, that lets me figure out whether this is a good pump to use or not. And so if I plot that full performance curves, my head and my efficiency, those are kind of the important ones. Where the head curve and the system curve intersect, that's called the operating point. In other words, if I set up this particular pump at this particular flow rate, so whatever this performance curves are, that's for some particular rotational speed, not flow rate, some particular rotational speed, some RPM value, and some pump itself gives me this curve. If I make that pump operate in my current system, it's going to operate at this flow rate and at that value of the head loss. So that's my operating point. That's what's going to happen if I actually hook up this pump. What I want to have happen is that I want this operating point to be close to the maximum efficiency of the pump itself. So in this case, this pump would be pretty good because the maximum efficiency happens very close to my operating point. My operating point, I'm going to be at very close to maximum efficiency. So this will be a very suitable pump for this particular system that I want to realize. Sometimes it's useful to have multiple pumps, so instead of just having one big pump, you can have two small pumps to accomplish the same thing. So if you have two pumps, you can place them either in series, so right back to back from each other, or in parallel, so across two different pipelines. So series or parallel, to provide additional head or flow capacity, depending on which way you do it. So in series, you get a head that's added at a constant flow rate, so same flow rate, but you can basically double the head or pressurize that you can get out of your system. So with one pump, I get this head curve here. If I have two pumps in series, so back to back, they have to have the same flow rate because again, conservation of mass can't go anywhere. So my flow rate's the same, but I get it twice the head because each pump does basically twice the amount of work being done because of twice the pumps. So I get twice the head. Essentially, this distance just doubled. For parallel, I have the same head, but I increase the flow rate. So flow rates are added at a constant head. So instead of adding, so here series, I basically added my y values together. Here I'm basically adding my x values together. So I have twice the flow rate essentially. So at this head, if I look at this flow rate, I then have twice the flow rate for two pumps. And whatever this flow rate is, twice the flow rate for two pumps. So time for an example. I have a centrifugal pump operating at 1750 RPM set up in the system. So basically pumping water, taking from this reservoir, pumping up somewhere else. Doesn't really matter where else it goes. Water level in the reservoir, point 1 is 3.5 feet above the pump center line. So this total distance is 3.5 feet. Inlet line of the pump, I have 6 feet of 5-inch diameter straight cast iron pipe. So that's this pipe here. Total length is 6 feet, 5-inch diameter. Then I have the sharp edged entrance. So this entrance into my tank, regular flange 90-degree elbow. This guy down here. Fully open gate valves. There's a valve in there as well that I didn't draw. I want to calculate the net positive suction head at a volume flow rate of 1,000 gallons per minute of water at 80 degrees Fahrenheit. So for the net positive suction head, I want the total head at the suction side of the pump. So basically what I want is the total head at point 2. So I'm going to set up the energy equation between point 1 and point 2 because I know stuff at point 1 to find that total suction head at point 2. So P1 over gamma plus V1 squared over 2G is plus Z1 is P2 over gamma, V2 squared over 2G plus Z2 plus my head loss. You may be asking why I don't have a pump on this side, and that's because between point 1 and 2 there is no pump. The pump comes after point 2, so no pump in this equation. Here P1 is atmospheric pressure, V1 is approximately 0, again assuming this tank's pretty big, so the water level goes down fairly slowly. I'm going to set Z2 equal to 0, which means that Z1 is 3.5 feet. And then finally, V2, my velocity in the pipe, is the flow rate divided by the area, 4Q over pi d squared. My Q is 1,000 gallons per minute, diameter of 5 inches, but I want that in feet, so 5 divided by 12 gives me feet. And speaking of proper units, gallons per minute, I want to convert that into feet cubed, so 0.134 feet cubed per gallon. And per minute, I want it in seconds, so 60 seconds per minute on the bottom. Gives me a velocity in that pipe of 16.4 feet per second. Then the last thing that I need for that equation is the head loss. So my head loss, going back to the pipe lessons, I have a combination of major loss and minor loss. So my major loss, FL over D times V squared over 2G, and V2, velocity in my pipe. So to find the major loss, I need the Reynolds number, the velocity diameter over kinematic viscosity of the water. So velocity of 16.4, diameter of 5, divided by 12, want that in feet. And then kinematic viscosity water at 80 degrees Fahrenheit, I can look that up in a table. And I have 9.27 times 10 to the negative 6 feet squared per second. Gives me a Reynolds number of 737,000. It's turbulent, so I'm also going to need to know the relative roughness. So again, find that for this cast iron pipe, 0.00085 feet. Which gives me the relative roughness parameter, epsilon over d, 0.00204. Then with those two values, I can now use the Moody chart or the equations that we saw a few weeks ago, and it gives me a friction factor F of 0.0237. So that's going to be for the major losses. And then for the minor losses, I need all the minor loss coefficients for all my various minor losses. I have the entrance, have the elbow, and have the fully open gate valve. So look up all those values. So for the sharp edge entrance, I have a K value of 0.5. For that 90-degree flange regular elbow, K value of 0.3, and then fully open gate valve 0.15. Grand total all of those is 0.95. And so my total head loss, FL over D, major loss, sum of K minor loss, all times V2 squared over 2G. So F 0.0237, length of pipe 6 feet, diameter 5 over 12 in feet, then sum of my K values 0.95, all times my velocity 16.4 feet per second squared, divided by 2, and G of 32.2 feet per second squared. Grand total head loss is 5.39 feet. And now that we know everything for the energy equation, we can set up the equation for the net positive suction head, NPSH, which is the head on the suction side, P2 over gamma, plus V2 squared over 2G plus Z2, that's my head on the suction side, minus my vapor pressure head. Now what I'm going to do, instead of calculating these things, because I don't know what P2 is, instead of calculating at point 2, I know that this is the same stuff at point 1 minus the head loss, just from the full energy equation. And I know all that stuff at point 1, so my net positive suction head, I'm going to use point 1 to calculate it, minus the head loss, minus the vapor pressure. And so at point 1, P1 is atmospheric, V1's gone, 0, still have the Z1, minus head loss and the vapor pressure. Vapor pressure of water at 80 degrees Fahrenheit is 0.507 psi. Get that from table B1. And so putting all those numbers in, net positive suction head, I have 2,116 pounds per square foot, atmospheric pressure, divided by 62.4 pounds per cubic foot for water. Z1 was 3.5 feet, head loss 5.39 feet, and then my vapor pressure, 0.507 psi. I want to multiply that by 144, so I want to make sure that's in PSF. And again, divided by 62.4, grand total net positive suction head and PSH of 30.9 feet for this situation. Little note on that, that's a good thing. Generally for these centrifugal pumps, you want to have a net positive suction head 10 or higher. Kind of makes you, gives a nice sort of safe range where you don't have to worry about cavitation. Anything less than 10 might be a bit of a worry. So second example, have a pump operating at 1170 RPM, impeller diameter 8 inches. This thing has a shutoff head of 25 feet of water, same operating speed, head of 21.9 feet of water, occurs at a flow rate of 300 gallons per minute. I want to find the operating point for this pump given that system curve shown down there. So that's some sort of system. Again, it has this quadratic sort of head rise with respect to flow rate. And so I want to find where the operating point is for this particular pump. So we're basically given two data points for this pump and its performance curve in terms of X, Y values, in this case Q and H. So at a Q of 0 gallons per minute flow rate, have a shutoff head of 25 feet, and at a flow rate of 300 gallons per minute, have a head of 21.9 feet. So the head curve, just like the system curve, is relatively quadratic. Difference being that system curve goes upwards, head curve generally goes downwards, but we can still fit these two data points to some function, similar to what we had for the system curve. H is A plus B Q squared. Using this first data point, it's fairly obvious that A is 25 feet. Then we can use the second data point to find B. So B is H minus A over Q squared. So H in this case 21.9, A which is found to be 25, and Q squared, 300 squared, gives me minus 3.44 times 10 to the negative fifth as the value of B. So plugging A and B back into my equation, I get an equation for my pump curve. H is 25 minus 3.44 times 10 to the negative fifth times Q squared. And this will give me an H in feet when Q is in gallons per minute, which is what my curve actually has. So H is in feet, Q was in gallons per minute. That's why I didn't bother doing any unit conversions. I want to keep them in these units because that's what is plotted down there. So that's my equation. If I actually plotted that, my green line is that curve. I can see that these two curves intersect roughly at a flow rate of 510. If I drew this a little better, I drew it in Excel in the actual lecture notes. I want to look at that so you can actually see better what's actually happening. But intersection point, roughly 510 gallons per minute, roughly a head loss of 16 feet, and so that will be my operating point for this situation.